this module, we are going to talk about Border Gateway Protocol, or BGP. And BGP is possibly one of the most misunderstood networking protocols in existence. So in this short introduction, we're going to talk about what is the BGP, what is the purpose of BGP. We are going to explore what are the autonomous systems. We are going to take a look at the role of BGP in the external and internal routing from the perspective of an autonomous system. We are going to talk about the routes and attributes, and we are going to quickly go over the best path selection process in BGP. If you read the documentation and the training material provided by various network vendors about BGP, they are quickly going to introduce the concept of BGP being called the path vector routing protocol. Now, what does that mean? Now, I don't know either, because they never actually explain what this means. Now, there are different interpretations that I have understood and that other people have understood. So from now on, I'm not going to refer to BGP as the path vector routing protocol. I have introduced this concept only because you are going to see this in the books, but I'm not going to expand on this. I'm going to give you my vision of BGP. I'm going to explain how BGP works, what it's used for, and you are going to make your own determination what the path vector might actually mean in plain English. The way I like to think of BGP is that it is actually a policy implementation system, a policy implementation protocol. Now, what does that mean? That simply means that BGP is a technical means to an end. It's a technical method of implementing business decisions. For example, we want to send traffic there because it's less expensive than sending the traffic there. Sending the traffic over this path is going to result in slightly shorter delay and better performance for our applications, which is going to allow us to process more transactions per second than sending the traffic, say, over that path there. Those are all relatively non-technical or business decisions. And with BGP, we have very, very good control where we want to send the traffic and to some degree where we want to receive the traffic sent to us. So BGP is primarily an implementation of policies. Now, as you might imagine, these policies, these business decisions where we want to send the traffic, where we want to receive the traffic, could get very complex and very involved. And that is the part about BGP that is the scariest when you first encounter it. When you look at all the possibilities in BGP, you are quickly going to realize that, oh my God, I'm never going to learn how this works. Well, rest assured that it is actually not that complicated. If you approach BGP from the right angle, it is an implementation protocol for different policies. All you have to do is figure out what is the policy that you are trying to implement and find the best tool to do it. I will talk about this in greater detail later on. But what is BGP other than the policy implementation system? Well, it is really the routing protocol of the internet. What I mean by that is it is the routing protocol that is running between different network carriers. Network carriers are large network operators, the internet providers, the network integrators, and so on, that carry vast majority of internet traffic. They are also the content providers, the large search engines, the social media, websites, and so on. These are all the networks. These are all good candidates to run the BGP. But also there are enterprises, large, medium, small, that also use BGP with their routing when they connect to their ISPs, to their network providers. And they do that mostly when they want to be multi-homed, when they want to be connected to more than one carrier in order to provide redundant connections. And this is also a very good candidate here, or the scenario when we might want to consider running BGP. One thing about BGP that is incredibly important is that it is virtually infinitely scalable. I remember when I was first learning about BGP, I was reading a particular book, and it was a book from Cisco Press that was called Internet Routing Architectures. I highly recommend that book. It is a little bit dated right now, but it's a very, very good read. And one of the sentences in that book really made me laugh. It went something along the lines of, at the moment of writing this book, there are almost 25,000 routes in the routing table in BGP, and some people estimate that eventually they may grow to more than 50,000 routes in the BGP table. And I was laughing because when I was reading that, I was working for an ISP, and I looked in our BGP routing table, and we had about 75,000 routes. Just before recording this particular segment, I looked at one of the routing tables on the BGP routers, and I saw 480,000 routes and counting, and these were only IPv4 routes. Now, mind you, between the time when I first studied about BGP, which was back in 1998 and 99, up until now, BGP hasn't changed that much. Yeah, there have been some improvements in how the particular implementations of BGP are done by different vendors, but the protocol itself hasn't really dramatically changed. It's still in its BGP version 4 instance, and it can carry not only 480,000 IPv4 routes, but there are also IPv6 routes. There are tens of thousands of those routes, and counting. That number is also growing. And not only the number of routes, but the BGP routers in the world, they count in tens of thousands of nodes, if not hundreds of thousands. So how does BGP manage this scalability? How does it grow to such large sizes? Well, it is able to do that because not all nodes are connected to all other nodes. So we don't have a full mesh of these BGP speakers. There is some resemblance of hierarchy involved. A founding block of understanding BGP hierarchy is understanding autonomous systems. So what are autonomous systems? Well, one of the definitions that I like is that an autonomous system is a network or a collection of networks under the same administrative control. Now, in plain English, what that means is that autonomous system is a network or a group of networks that share the same internal routing rules or the common routing policy. What this usually translates to is that we have a single organization that controls this network or a group of networks, or we might even have multiple organizations or multiple internal organizations that are maintaining parts of the network, but when viewed from the outside world, this one network is perceived as a single entity. And we can say that this single network in the hierarchy of BGP is perceived as a single node. Let me explain this in a little bit more detail. Let's imagine a network that consists of several routers. Now, we don't care how many of these routers are, but let's say that all these routers here are under the same administrative control. Now, let's imagine that we had any number of these networks in existence in the world or in our internet that we are trying to sort of emulate here. So now we have all these networks, and we don't really know how these networks could be interconnected. We could have any number of interconnections between these networks that form basically the internet. So we could have the full mesh, or we could have partial mesh, or we could have any sort of layout that we can imagine. Now, if we take a look at this network here, all these entities here, all the routes and all the routing policies inside one of these, well, they look like cookies or pizzas. Here, the routing policy within all of these is the same and perceived by the outside network as a single entity. So what we can say is really that our network here consists of 6 entities that are somehow interconnected. So let's say that this is how our connections look like. What we are hiding here from the rest of the world is the internal complexity of the network. What this entity here, the autonomous system, is telling to this autonomous system here. And this autonomous system here is that certain networks, that certain paths are reachable if you would send the traffic to it, but what we are hiding is the internal complexity. These nodes here don't need to know what is happening inside this autonomous system. They just need to know that if they send the traffic to that autonomous system, they can probably reach this autonomous system here. These entities or autonomous systems are in the BGP routing identified by a number. This number is called the autonomous system number, or sometimes simply ASN, or the AS number. There are two forms of the AS numbers. Traditionally, the AS number was 16 bits long, which gave us possible values from 0 to 65,535. However, there are actually more than this autonomous systems in the world today, so we started running out of autonomous system numbers. Luckily, unlike the solution for running out of IP addresses, running out of autonomous systems wasn't such a big deal, and you didn't probably hear about it in the news. What happened was that the address space for the autonomous system addressing was extended from 16 to 32 bits, which gave us not only 65,535 possible numbers, but, well, I can't even read this number. I'm guessing that this is 4,294,000,000, oh, actually it's 4,294,967,295 routes. So a lot of routes. So whenever you see autonomous system number that is in this range, you know that whatever router, whatever device this autonomous system is configured on needs to support 32-bit autonomous system numbers. Now, not all routers and not all versions of iOS software do support 32-bit autonomous system numbers, but most of the modern ones do. These new autonomous systems, the 32-bit numbers, can be represented using two different forms of notation. Using something that is called AS plain notation, where we simply write the number, so this would be AS plain. However, there was a brief period of time, and in some versions of iOS, depending on what you are using, you might see slightly different notation, something called the AS dot notation, where basically the autonomous system number, this large number when it was higher than 16 bits, was divided into two parts. The first part and then the second part. So using this AS dot notation, for example, the autonomous system 65,536 would be represented as 1.0. This is no longer recommended way of representing 32-bit numbers, 32-bit AS numbers, so we are now going to be using only the AS plain. So you don't actually have to worry about this older format, but you might encounter it depending on the iOS version that you are using. And AS numbers come in two different shapes and forms. Now, two different shapes and forms depending on which number you are planning on to use. Similarly to IP addresses, where we have globally assigned unique IP addresses that you need to obtain from a particular organization called the Regional Internet Registry. In the United States, it's called ERIN. In Europe, it's called RIPE-NCC. In Asia Pacific region, it's called APNIC. In Africa, it's called AFRINIC. And in Latin America, it's called the LACNIC. So these regional internet registries, they have certain blocks of IP addresses assigned to them by IANA, which is Internet Assigned Assigned Numbers Associations, or something along those lines. I really can't remember what that acronym stands for. But the idea there is that IP addresses, if they are globally unique, they need to be assigned by these regional internet registries. Now, if you wanted to use some IP addresses in your institution, in your organization, without obtaining them from the regional internet registry, you would use private IP addresses. And these are our 10.0.0.0/8 or 172.16/12 or 192.168.0.0/16 IP address ranges. Similar concept exists for autonomous system numbers. You can't just use any number you like on the global internet. If it's globally unique, if you're going to participate in the global internet, you need a globally unique autonomous system number, and this is the number that will be, similarly to IP addresses, assigned by a regional internet registry. If you wanted to use autonomous systems inside your organization and not be visible outside of your organization, you can use the private range of autonomous systems. For the 16 bits autonomous systems, 1023 autonomous systems have been reserved for the private use, and they come from the range of 64,512 to 65,534. If you wanted to use a private 32-bit number, well, you would have a lot more at your disposal. If I'm not much mistaken, you are going to have 94,967,295 of them available. So unlikely that you're ever going to run out of them, and they will be coming from this range. From practical perspective, for practical purposes, this is the range that you should probably remember as the private range, and this one here, well, good luck remembering what the actual range is, but anyways, here it is for your reference. BGP as a protocol can serve two roles. It can be used to carry the information about the external routing, and here by external we mean the routes that have been learned from outside our autonomous system. Or it can be used to carry those routes inside our autonomous system. When we are configuring BGP, when we are running BGP between the two autonomous systems, we usually say that we are dealing with external BGP routing. When we are carrying the routes inside our autonomous system, we say that we are running internal BGP routing. So what is the difference between internal and external BGP routing? Well, first of all, the definition of an internal or an external is whom are we peering with? And when we say peering, that's the relationship that is established between BGP routers. When two BGP routers are configured to exchange the routes between themselves, we say that they are peering. They are forming a BGP peering session. This BGP peering session is considered to be external when the neighbor is not configured to be in the same autonomous system as we are. There are some rules that govern this external peering, and one of the most important ones is that by default the external neighbor needs to be directly connected to us. Now, why would this be? Why would the external peer need to be directly connected to us? Well, the reason is that the whole idea of BGP is that it's the internet protocol, it's the routing protocol that holds the internet together. And the assumption is that between different autonomous systems, there are no other routing protocols running. If there is no other routing protocol running between the autonomous systems, how do we then speak with our neighbor? Well, if it's directly connected. As we will see in a couple of examples that I'm going to go through, this rule is not really a hard rule. You can still have external peering sessions with the neighbors that are not directly connected, but you do have to do some extra configuration steps to make that happen. By default, the direct connectivity is required. Now, the major loop prevention mechanism in BGP when we are dealing with the external session is a BGP attribute, and I'm going to talk in more detail about BGP attributes in just a minute, is the attribute called the AS path. The AS path is the ordered list of all autonomous systems in which the prefix advertised has been into. So how does this loop prevention work? Well, very simply, when we are receiving a prefix from the neighbor, from an external neighbor, we are going to look into the AS path list. If we see our own AS number in the AS path list, we are going to reject this update. We are going to reject this prefix because it is looping. It is trying to come back into our own autonomous system. Now, as you might imagine, BGP being the policy implementation protocol, this particular behavior can also be changed. We can configure our neighbor to accept even those routes that have our own AS number in the AS path list. So what makes the internal peering sessions then? Let's take a look at them. So the internal peering session, the first thing that you need to have in mind is it is not designed to replace the IGP. It's not designed to replace the internal routing protocol. It works together with it. Now, what's the whole idea here? Well, the whole idea here is that if we have an autonomous system, and this autonomous system has some routers in this autonomous system that might be interconnected any way we like, and then we have another autonomous system. Now, let's say that there is some route in this autonomous system here. Let's say that this is a network N. When this network N gets advertised, gets injected into this router here, how do we get this route to go across this autonomous system? So let's say that here in this autonomous system, except on this router here, we are only running OSPF. Well, that's a simple thing. Here we are going to advertise this route in OSPF. On this router here, we are going to redistribute it into BGP and advertise it to our neighbor. Now, on this side here, when this route here has been learned in BGP, how do we then advertise this route to these two neighbors here? Well, there are two ways we can do that. We can obviously, let's say that here on this side we were running EIGRP. We could obviously redistribute from BGP into EIGRP, but that is a sure way to create a disaster in your autonomous system. Why? Because these routes that we are receiving here, I used an example of a single route, but remember what I said, there are about 450,000 routes, or even more, 480,000 I believe I said there were. So 450 plus thousand routes. If you redistribute this into EIGRP or OSPF or any other routing protocol, any internal routing protocol for that matter, you are sure going to collapse this routing protocol here, because these protocols are not designed to scale to these large number of routes. So how do we then provide the reachability from this router to these routers here? Well, we can use BGP inside our autonomous system to advertise these routes. Now, mind you, that these routes here, that they are ultimately, at one point, they were external routes. They were learned from an external peer. But now we are going to advertise them internally to our neighbors. We are still going to use EIGRP for the internal routing reachability, but due to the nature of BGP, due to the possible size of this routing table, we are using BGP internally in our autonomous system to avoid the redistribution from BGP into our IGP. So we can really say that the whole idea of the internal BGP is still to carry the external prefixes, but now throughout the autonomous system. One more thing that I would like to point out is that at this point here, when this route has been advertised, when this route N was advertised from this neighbor to this neighbor here, it was considered to be an external route. Why is it considered to be an external route? It's considered to be an external route because it was learned from an external peer. But when this router here advertises this route, this externally learned route, when it advertises it to these two peers, at this point here, this route is considered to be an internal BGP route. Now, this might be a little bit confusing. Now, let me redraw this diagram here. Let me zoom it up a little bit. So here is the boundary of our two autonomous systems. Now, let's say that here I have multiple routers that might be peering with this one. So here we have R1, here we have R2, R3, and R4. Let's say that this one here is the AS65000, and let's say that this one here is AS65001. So they are obviously different autonomous systems, and there is the peering between these two here. So when this route here is being advertised to this peer, we know that our peer was in different AS. And this is what makes the route external. Now, when this route here gets advertised to these routers here are in the same AS. So the peer from which we are learning this route is in same AS. And this is what determines whether the route is internal or external. We don't really care at this point here that this route was originally learned from an external peer, from a different autonomous system. In other words, we don't care about the originating autonomous system. This would be the originating autonomous system, but it would in this case also be the peer autonomous system. On this session here, on this route exchange, the peer autonomous system is the same as ours. That means that all the routes learned from here are considered to be internal routes. Now, this is very, very important concept to master because of the loop prevention that is required or that is used inside the autonomous system. Now, we know that between the autonomous systems, we are going to be using the AS path attribute. However, inside the autonomous system, we are going to be using something that I like to call the split horizon. The rule there says that BGP router does not re-advertise internally learned prefixes to other internal peers. You can't see this here, but it says internal peers right there. Now, what does that mean? That means that let's say that we had a BGP peering session between R3 and R4. Now, when we learned this route, it was at this point an internal route. Remember, we don't care where it originally came from, we care where we learned it from, and we learned it from the peer that was in the same AS. That means that this route will not be re-advertised to R4. The same thing happens here. R4 learned this route from an internal peer. Now let me disappear here for a second. So R4 learned the route from an internal peer, which means it will not advertise this route to another internal peer. There is a very, very good reason why this happens. And the reason why this happens is that the AS path attribute that is updated when the route is advertised between the autonomous systems is actually not modified inside the AS. And if it's not modified inside the AS, that means that it cannot be used for loop prevention. So what we could have is a situation inside an autonomous system where we could have the route that was, say, externally learned by one router here. So let's give these routers names, R1, R2, R3, R4, R5, and R6. So we could have a situation that this route here gets advertised here, then advertised here, 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 and back to R1, which means that it would suddenly become an internal route, and it could, because, you know, in BGP we can modify any policies that we like, we could make this route be better than this one. By default it won't be, but we can make it. So that means that we're going to advertise this route and so on, and we can easily create the loop. So what BGP simply says is, if you have learned the route from an internal peer, do not advertise to other internal peers, which does create a sort of a problem in this scenario here. So let me clean this up a little bit to show you what the problem is. If the rules are followed and we say that when the internal peers, and these would be internal peers, learn the route, they will not advertise this route to other peers, which means that routers 3, 4, and 5 will not have reachability with this network advertised here by default. This is where the next part of internal BGP differences comes into play. What is that next part? Well, that means simply here that there is going to be a full mesh as a workaround, full mesh of peering sessions. So what we are going to use as a workaround here is we are going to have a peering session from R1 to all these routers here. Then we are going to have this peering session here, we are going to have this one here, we're going to have this one here, and this one here. I believe that I covered all of them. I think I have. So how can then R1 peer with R4? They are not directly connected. Well, another piece of the puzzle. For the internal peerings, because BGP works together with IGP, so I believe that I may have mentioned it here, so I didn't, but BGP does not replace IGP, it works together with the IGP. Direct connectivity is not required for peering sessions because this router here, using the IGP protocol that we are running here, which could be OSPF, it could be RIP, it could be static, it could be EIGRP, anything that we have as our IGPs, anything that we can use as IGP is okay to use as the routing protocol here. R1 will know how to reach R4. So they could have a direct peering session even though they are not physically directly connected or even logically directly connected. How does that work? Where should then this peering session be established with? Between which of these interfaces here? Well, for internal peering sessions, it's the most common configuration to actually form these peering sessions between the loopback interfaces on the routers. Why? Because in that case, if we have the peering between the loopback on this side here and the loopback on this side here, we don't care which one of these physical interfaces are up. As long as one is up on both sides, we are probably going to have the reachability because we have the ring structure here. If we have two failures, then obviously there is going to be a problem, but I'm just using this as an example here. So for internal BGP peering rules, we know that there is going to be this kind of a split horizon. If you have learned from an internal peer, don't re-advertise the route to another internal peer. We don't need to have direct connectivity between the neighbors, and we have a full mesh as a workaround. But there is a problem with using full mesh. The problem with full mesh is if we have a really large autonomous system, and remember, the primary users of BGP are large international carriers or national carriers or large ISPs, and they have large number of routers. And the full mesh means that there is going to be n times n minus 1 over 2 number of peering sessions. And that can grow dramatically, and maintaining these peering sessions can become a challenge. So BGP offers us two possible solutions for a scalability challenge. One is using so-called route reflectors, and the other one is using so-called confederations. I will talk about them in great detail when I talk about internal BGP peering a little bit later on. Many times so far I have mentioned routes and attributes in BGP, so let's talk about them now. In BGP, the routes are carried in updates that are generally speaking called NLRIs, or the Network Layer Reachability Information. In its most generic form, NLRI consists of two parts. One is the route and prefix, and the other one is the set of attributes that describe that route and prefix. What I mean by route and prefix is the network and really the prefix length. So this is what is in the route, and then the attributes is a collection of different BGP attributes. Now, not all BGP attributes are the same. They can be divided into several categories that describe attributes themselves. First of all, the attributes are divided based on the implementation requirements, and these are further subdivided into the well-known attributes and the optional attributes. Well-known attributes are those attributes that must be understood by the BGP implementation, by every BGP implementation. Optional attributes are exactly that. The BGP implementation, the vendor implementation of the BGP code on devices, does not necessarily need to understand or do anything about those optional attributes. Well-known attributes are further divided into two categories: the mandatory updates and the discretionary updates. The mandatory attributes, they must be present on every single update. So every network layer reachability information must carry with itself those mandatory BGP attributes, well-known mandatory ones. The discretionary ones can or may not exist on a particular update, but every implementation needs to know what to do with them if they appear. Furthermore, all of these updates, well-known or optional, are divided based on their scope or network reach, how far in the network this attribute will go without being explicitly or implicitly filtered out. Actually, implicitly filtered out. Some attributes cannot go across certain boundaries. Now, there are, officially speaking, two types, which are transitive and non-transitive. Transitive simply means that the attribute will be carried across the autonomous system boundaries. That means that if we had AS1 with a certain prefix that had a certain attribute, by default, this prefix will be carried over into autonomous system 2, and by default will be carried into autonomous system 3, and so on, so on, and so on. So this is what the transitive means. Non-transitive means that a particular attribute that exists in AS1 will not be carried over when this prefix is advertised into another AS. So if this was AS1 and this is AS2, and there was a certain attribute that existed on this prefix, it would actually end its life here. Now keep in mind that even for the transitory attributes, we can change them. This is very different than, for example, the flooding scope of LSAs in OSPF, where we cannot change anything in the LSA within the flooding scope. With BGP, we can modify attributes pretty much freely. We can do whatever we like. It's just how the default behavior is. Now, another thing is that we cannot make non-transitive attribute go across the AS. It is not going to happen. So it will stop here, but we can change, for example, the transitive attribute as it goes here. So whatever that transitive attribute was in this AS, on this peering session here, we could change it. Or even internally in the AS, we can modify these attributes. The third category of scope is something that is, you're not going to find this in many books, is something that and this is why I put it in parentheses here, are the local attributes. These are usually vendor specific, and in Cisco's implementation of BGP, there is only one locally significant attribute. So these are, technically speaking, non-transitive, but they are even more than that. They will not leave a particular device, a particular router. So what are some of these attributes? And keep in mind, I'm going to go in great detail about every single one of them. So now I'm just going to give you a quick overview of these attributes. So when it comes to the well-known mandatory attributes, there are 3 of them, and this is something that you absolutely have to know. Next hop, AS path, and the origin attribute are the mandatory attributes. All 3 of them, as you can see, are transitive attributes. Well-known discretionary attributes, and this is not a complete list, there are others, these are just examples, are the local preference and the atomic aggregate. Local preference is non-transitive and the atomic aggregate is transitive. Some of the optional ones are wait, and this is a non-transitive local, so this is a Cisco proprietary attribute. There is a community one, which is transitive. Multi-exit discriminator, or the MED or metric, has many different names, this one. This is a non-transitive one, and I used a little asterisk here to indicate that this is a really very specific non-transitive attribute, in a sense that it can be set in a particular AS. So let's say in this AS1 here, on this peering session here, I can set the MED on this peering session, and it will be visible inside this AS2, but it will not leave when this route is advertised to, say, AS3. So it can be communicated across the autonomous system boundary, but it will not be communicated outside of the boundary, outside of the AS into which it was advertised. So this one is, technically speaking, non-transitive, but it does have this special behavior. Then we have the originator ID, which is non-transitive, the cluster ID non-transitive, and etc., etc., etc. There are many different BGP attributes, but these are some of the most common ones, some of the most important ones. If you cannot remember all of these right now, and if you may be struggling with this, just remember the 3 mandatory ones. These will always be on every single BGP update. All these attributes don't exist just for fun. They are used by BGP in the best path selection process. Unlike other protocols that we have examined so far that use relatively simple metrics like EIGRP's composite metric or OSPF cost, BGP doesn't really have a fixed metric, a single entity on which it decides which route is the best, given that it has multiple routes for the same prefix. What BGP uses is a very elaborate best path selection process that goes through the list of these attributes and uses them in the way that is unique to a particular attribute being examined. This list here that I have listed is processed sequentially. Here at the end, I'm just going to start at the end. It might be a little bit unusual, but it will make sense in a second. At the end, I have simply said that we have a bunch of tiebreakers, and here you have the link where you can find a more detailed description of this process. Now, why did I say that there is going to be a bunch of tiebreakers at the end? I'm going to talk about this in great detail, but really, this is the most important part of the BGP best path selection process. If by this stage the BGP has not found out the best route, it is going to go through the laundry list of items to determine which route is the best. So let's go through this best path selection process as it is right now. The first thing that I'm going to say is that it is not officially part of the BGP best path selection process, but it is going to be the first thing that is going to be considered. I sometimes call this step 0. Is the next hop reachable? Now you remember that the next hop is the mandatory transitory attribute that exists on every single BGP update, mandatory transitive BGP attribute. So this attribute always exists. The first check that is going to be performed is it in the routing table? If it's not in the routing table, the route is not eligible to become the best route, and this is the end of the process. Now, if the next hop is in the routing table, and this is the only check that is performed, then the BGP is going to go through the list of these items, comparing multiple routing updates, multiple network layer reachability informations for the same prefix. Now you remember that NLRI consists of the prefix and the attribute. So let's say that we have the same prefix 192.168.0.0/24, and we are learning this from two different sides, from two different peers, or whatever the scenario might be. So for the same prefix, two different updates with a different set of attributes. The first thing that is going to be taken into account, and remember this is Cisco proprietary, is going to be the weight. The highest value will win. If the weight is the same, then the value of the local preference will be considered. Again, the highest will win. If these two are the same, BGP is going to prefer those routes that were injected locally by that router versus those routes that may have been learned from another peers. Given that all these three are the same, in that case the AS path attribute will be considered and the shortest one will win. So think of the AS path in this context as a hop count. Smaller the hop count, better the route. If all these four are the same, then the origin attribute. Origin attribute is an attribute that describes how the route was injected into the BGP domain at its originating point. So with the origin, the lowest value is going to be concerned. There are three values for origin that you might see. They are going to be 0, 1, or 2. 0 is going to be IGP, 1 is going to be EGP, and 2 is going to be incomplete. Now, these are going to be represented in iOS as lowercase I, lowercase e, or the question mark. And this is the order of precedence, IGP over EGP over incomplete. Then, given that these are the same and a certain set of conditions that I'm going to talk about in great detail when I examine this in more detail. Right now we are just going through the overview. If those conditions are met, the multi-exit discriminator or the MED or the metric, multiple names for the same attribute, is going to be considered, and in this case the lowest value wins. In step 7, the route that has been learned from an external peer is going to be preferred over the route that has been internally learned. So we are going to prefer the external over internal peer. And I should point out that this has nothing to do with the administrative distance of the routes. If all these 7 are the same, the lowest IGP cost to the next hop will be considered. So whatever is the cost to reach the next hop attribute in the routing table, and the lowest value will be used. If these are the same, as I said, we are going to go through the list of multiple tiebreakers. So this is a general overview of BGP best path selection process. I'm going to go into this and we are going to go through every single attribute in greater detail in one of the subsequent videos. Right now, as I said, this is just an overview. To end this quick overview of BGP, let's go over the basic configuration of it. BGP in iOS these days can be configured using two different methods. One that I'm going to describe here first is something that is sometimes called either traditional or the flat BGP configuration. It's called flat because when you look at the configuration, all of the commands appear to be in a single level of hierarchy. We are going to configure the router BGP, then we are going to specify whatever is our own AS number, and here we can specify various settings, various configurations that are going to influence the behavior of BGP from a global perspective on that router. Like, for example, the default timers, what is going to be our BGP router ID. So I use this as a common thing that you might want to set up, and simply things like that that don't really relate to any particular BGP neighbors. So here we are going to specify some of the BGP parameters. Then we are going to have the definition of one or more neighbors. Unlike interior gateway protocols, unlike EIGRP, OSPF, RIP, SIS, and all the others, BGP is technically speaking not enabled on per network or per interface basis. The way BGP is enabled is per neighbor basis, so neighbors need to be defined manually. This is not always true. Some of the versions of the iOS and iOS XR, for example, do have a capability to configure BGP on the entire subnet, for example. But these are special configurations that have something to do with scaling the number of peerings that you might have on a single subnet. And the situations for this are so-called internet exchanges, where we are going to be applying the same policies to this large number of neighbors, and we don't really know in advance who our neighbors are going to be. But when BGP starts working, it is always going to operate on this per neighbor basis. The policies are always going to be maintained on a per neighbor. It's a logical way of thinking about it. There are some optimizations in the iOS that actually can group neighbors together, so-called update groups, that can maintain the relationship with multiple neighbors and then apply the same policies and behaviors to those groups of neighbors. But this early in learning about BGP, those are far too advanced technical details. So at this point, you should really be thinking about that BGP maintains the neighbor relationships on an individual neighbor basis, and that all neighbors need to be strictly and manually defined in the configuration. How do we define the neighbor? Well, there is a mandatory command. One command needs to always be there, and that is going to be neighbor and then the IP address of the neighbor, remote AS, and then specifying whatever the neighbor's AS is. Now, given that this number here is the same as our own AS, iOS will treat this neighbor as the internal neighbor. If this AS here is not the same as our own AS number, this neighbor will be treated as the external neighbor. In iOS, there is no need to configure anything extra to determine or to tell iOS how to treat this particular neighbor. And then we can specify any number of per neighbor options. So what are some of the common ones? Well, we can specify the password, and here we would say neighbor, whatever neighbor's IP address is, password, and here we would simply specify the password. We can use update source, and this is a very common configuration in internal peerings where we want to use loopback interface as the update source, or it can even be used for external peerings if we have non-directly connected neighbors. We can also specify send community, and I'm going to talk about communities later on. We can specify various filters, and here I have shown you how to, for example, use the route map called RM, either in the inbound or the outbound direction for filtering. We can use distribute list, we can use filter list. There are any a number of methods that we can use to filter the routes. We can also tell the BGP to, okay, this neighbor is configured, but don't actually form the session with this neighbor for some reason. We want to take it down temporarily, and then you would shut the neighbor down. You can also specify what timers you want to use. And for BGP, there are really three sets of timers, and these are keep alive hold timer and the minimum hold timer. I'll talk about them a little bit later on. So this is what is the traditional configuration or the flat configuration. And you can see that most of the settings in BGP are configured on per neighbor basis. One of the common things that you want to do in BGP is to actually advertise certain networks. And in BGP, the network statement is used for that. But network statement in BGP behaves very differently than the network statement in IGPs. What network statement in BGP does is it is going to look in the routing table on this router, and it's going to look for the exact match of this route. So this route needs to exist in the routing table already, inserted by some other protocol. BGP doesn't care which protocol that is going to be. And if it finds the exact match, that means that the network and the mask part need to match exactly, then this route will actually be inserted into the local BGP table. So it already needs to exist in the routing table before it gets inserted into BGP. So unlike IGPs, where network statement actually enables the protocol on a particular subnet, on a particular set of interfaces, in BGP it actually doesn't do that. In BGP you activate protocol on a per neighbor basis using the neighbor statements, and with the network statement you actually advertise the exact route that you want. You can also filter, or actually you can set some attributes on this route. So any number of attributes that can be modified, like for example the local preference, or you may want to set certain route tags. In BGP they are called the communities, and so on. You can do that with the route map here at the insertion point of this network. So in short, this is a very, very basic BGP configuration example using the traditional or the flat configuration. A slightly more modern way of configuring BGP is using address family based configuration. So as you will see, it's very, very similar to the flat configuration. We start by specifying router BGP and our own AS number. So far so good. Optionally, when you are doing this for the first time, you may want to run the command BGP upgrade-CLI. As I say, this is optional. You don't have to do this. What this command will do, it will take the existing BGP configuration and it will convert it from the flat configuration into the address family based configuration. You don't have to do it. iOS can also do this automatically. I usually actually do use this command. No particular reason, I just like to use it. Then we can specify a various global settings, and just like with the flat configuration, these would be, for example, the BGP router ID, it would be the various timers that we want to use per neighbor settings and so on. But for the BGP router ID, keep in mind that what can actually be done is that it can also be specified per address family. And address family can be IPv4, can be IPv6, it can be unicast, can be multicast, can be VPN-v4 used for MPLS VPNs, it can be any number of things. But here I'm just going to focus on using BGP for IPv4 routing. Then what we are going to do is we're going to specify the neighbor, and you remember there is one mandatory command, so we have to specify the remote AS. And then here we are going to specify any configurations that pertain to that neighbor that have to do with the BGP session. Now, what is a BGP session? It is how this TCP session is formed, how the BGP communication is formed. So these would be things like, for example, the password, the update source, shutdown, the timers. So these would be the session commands, and these would be specified in this part of the configuration. And then we're going to move into the address family configuration. So we're going to say address family IPv4 unicast if we want to configure the session for IPv4 unicast. By default in iOS, all neighbors defined in the global configuration are automatically going to be activated in that particular address family. So this command here is optional, and you will see it in the configuration, but you don't actually have to type it. I personally like to type it because that way I'm going to activate the neighbor even though BGP may have been configured not to activate these neighbors automatically, which is something that can be configured in this part of configuration here. The command for that is no BGP default IPv4 unicast. Now, then I'm going to specify a certain number, optionally, per neighbor policy options. What are the policy options? Any sort of route filtering, for example. If we are going to be if you're going to be changing the next hop attribute, there are commands that do that, like for example, next hop self or next hop unchanged. Anything to do with modifying the way learned and advertised routes behave is what BGP calls the policy options. So session options, they control the communication and they are going to be specified in the global configuration part of BGP. And anything that has to do with anything that influences how the routes behave, including, for example, route reflection configuration. I'm going to talk about that later on. This can be configured or should be configured in these policy options. Keep in mind that advertising the route is also a matter of policy. So advertising the route, network N with mask M, that behaves just like it does in the flat configuration, needs to be done under the address family, because this influences the fact that this route will be advertised with potentially these parameters in the route map. Let's now take a look at a very simple BGP configuration in action. What I'm going to do here is I'm going to set up just two routers, my R1 and R2, interconnected on gigabit interface 1 on this side, gigabit interface 1 on this side, and I want to run 192.168.12.0/24 network between them. There is going to be a loop back here and there is going to be a loop back here, but we'll get to loopbacks in a moment. So what I want to do here is I want to run BGP between these two routers here, and what I would like to do is run this, my R1, in autonomous system 65001, and let's say that I'm going to run R2, and there are going to be some other routers coming on later on in the subsequent examples. So this one is going to be AS65, let's say 2, 3, 4, for example. So I will have routers 2, 3, and 4 later on in this example, but right now I just want to have this basic session between them. So as a matter of exercise, given that this is AS65001 and this is AS65234, what is going to be the peering session between them? Is it going to be an internal peering session or an external peering session? If you answered external, you would be right. So let's go ahead and configure this. Again, as a matter of exercise, on this side here, I will use the flat BGP configuration, and on this side, I'm going to be using the AF-based configuration. So let's take a look at what we have to do. As always, first thing that we want to verify is the reachability between R1 and R2. What I'm going to do here on R1 is I'm going to say show IP route connected. What I'm looking for is 192.168.12.0 directly connected on gigabit 1, and I can see that. So let's make sure that I can actually ping 192.168.12.2, and I can see that I can ping it. On R2, I'm going to do show IP route connected, and what I'm looking for is 192.168.12.0/24 on gigabit 1, and I want to make sure that I can actually ping R1, and I can do that. So I'm going to start configuring BGP now. On R1 side, I'm going to say router BGP 65001. This is going to now start the process. The next thing that I'm going to do is a mandatory command. I'm going to say neighbor 192.168.12.2 remote AS 65234. Now this is going to define the neighbor. At this point, I don't actually have to do anything more on R1. So how can we see if BGP has been activated on R1? The best command to run for that is show IP BGP summary. Now, I should point out that because we are running flat configuration here, this would be the command that you would be running on all versions of iOS, and you're always going to get the same output. But there is a newer version of the command that is more recommended by Cisco to run that is going to produce the exact same output. And that command is show BGP summary, show BGP IPv4 unicast summary. And as you can see, the output that I have received from these two commands is exactly the same. So what I can see in this output here is that I have the neighbor 192.168.12.2 that has been defined. It is running version 4 of BGP, and this is something that you will always see. You can see the AS number that has been defined for the remote side, how many BGP messages we received, how many BGP messages we sent, what is the version of the BGP table, that's an internal number, and how many prefixes, how many NLRIs are in the input queue being received from the neighbor, or how many are waiting to be sent. When was the last time there was a change in the state, and we can see that the state never changed, and here we can see what is the state, and it says that the state is idle. Idle simply means we are either attempting to connect to the neighbor or we are waiting for the neighbor connection to begin. At this moment, really nothing there is happening. On R2, I'm going to be running the newer version of configuration. So I'm going to say router BGP 65.234, just as the same as before. And now I'm going to force myself to actually use the new CLI, the address family based. And I'm going to run BGP upgrade CLI command. It's going to ask me, am I sure that I want to do that? And my answer to that question is yes. Now, keep in mind that after you have done this, after you have activated the BGP, the new CLI, and there are two ways of doing it, explicitly like here, or simply just typing address family IPv4, done, that also upgrades the CLI. The moment you have upgraded CLI, either implicitly or explicitly like I did, this command is no longer available. So you don't really have to remember this command, it's not mandatory, but it's a good thing to keep in mind if you want to force yourself to use the new format. Then I'm going to define the neighbor. I'm going to say neighbor 192.168.12.1, remote AS 65.01, and the interesting thing is that this is going to be more than enough for the neighbor to form. So next thing I'm going to do, and we can see that the neighbor actually changed state to up. So let me show you how the configuration looks right now. So on this side where we have R2, this is how the configuration looks like. Now we can see here that there is a neighbor defined with the remote AS, and then under the address family here, we can see that automatically there was an activate command entered. On R1, the same configuration, so show run section router BGP, looks like this, simply neighbor and then the definition of the neighbor. So this is pretty much the only thing that we have on R1's configuration side. And if I repeat my show IPBGP summary command, I'm now going to see that some things have changed. I can see that certain number of messages have been received, certain number of messages have been sent. The BGP table version is still 1. We can see that the last change was 47 seconds ago, and now the state here says 0. This is now not the state. The states in BGP are transient states through which the neighbor formation goes through. I'll talk about it in a moment. But what we have here is now not the state of BGP, but how many prefixes have we actually received from the other router. And we can see that we have received 0 prefixes. We have received 0 prefixes because we have advertised 0 prefixes. Now, on R2, here I have used the new configuration mode, but I can still run that show IPBGP summary command if you are used to running it. But you should really try to make yourself show BGP IPv4 unicast summary. You should really force yourself to run the newer version of commands. And here I can see pretty much the same status that I have on the other side. Now, let's bring in some routes into this network. So how do we bring routes into BGP? Well, there are two ways. One is using the network statement, and the other one is simple redistribution of a certain protocol into BGP. I'm going to show you both examples. So on R1, what I'm going to do now is I'm going to go to router BGP 65001, and I'm going to say network, and I want to advertise the loopback interface. So what is my loopback interface? It's 172.16.0.1. So I'm going to say network 172.16.0.0 mask 255.255.255.0. I want to show you something. So now if I type in this mask for IGP configuration, this configuration here would actually cover this interface here. Let's see what happened in BGP. If I do show IPBGP, which is going to show me my BGP table, it's empty. Why is it empty? Because the network statement, you will recall, behaves differently in BGP. What I'm instructing BGP is to look in the routing table and look for the exact match for this route. So what I'm looking for is 172.16.0.0/24. Let's see our routing table. Do I have that route in the routing table? I do not. What I do have is 172.16.01. So this network statement will not do anything as it is right now into my BGP. So let's remove it. What I need to do is a network statement that matches my loopback exactly. Now, if I do show IP BGP, I'm going to see that I do have this route in my BGP table. And by now, it has actually been advertised to R2. Now we can see that the output of show BGP IPv4 unicast summary is a little bit longer, because now there is actually something in the BGP table. So we are going to have all this header information here. We're going to have information: what is our local BGP router ID, what is our local AS number, the table version and the main routing table version, you don't care about that. You're going to see how many network entries we have in the BGP table, and we can see how much memory it is consuming. We are going to see how many paths we have, etc., etc. So we're going to see a lot of information about the BGP table. But more importantly here, associated with our neighbor, now we are going to see information that prefix is received is 1. Why are we seeing this? Because R1 now actually advertised this prefix to R2. And if I do show IP BGP or show BGP IPv4 unicast, I am going to see that prefix. And if I do show IP route BGP, I'm now going to see that this route is actually in the routing table. Let's now go to R2 into our router BGP 65234, address family IPv4 unicast, and here I want to redistribute the loopback, but I want to redistribute only the loopback. How am I going to do that? Well, I need some sort of a filter, first of all. And the best filter, or actually pretty much the only one you can use in this case, is the route map. So let's do route map, and I'm just going to call it connected, and I'm going to say match interface loopback 0. Then I'm going to go into my router BGP, address family IPv4 unicast, and I'm going to say redistribute connected route map, and here I'm going to specify my route map con. So if I do show IP BGP, or actually let's use the new one, show BGP IPv4 unicast, what I should be seeing here is that 192.168.0.2 has been redistributed into BGP. If I go to R1, now if I do show IP BGP summary on this side, what I should be seeing that from R1 at this point, from R2 at this point, I'm actually learning one prefix. So here I have this one prefix learned, and if I do show IP BGP, I'm going to see that I have the locally injected prefix 172.16.0.1, and I have a remotely learned prefix 192.168.0.2. If I do show IP route BGP, I can see that this loopback now made it in to my routing table. So if I ping 192.168.0.2 source loopback 0, this should work. I have a connectivity between R1's and R2's loopback. So this is a very, very basic BGP configuration.